Good day, friends. Welcome to my channel lecture series on power electronics. In this lecture, we will discuss about three-phase half-wave controlled rectifiers. Three-phase controlled rectifiers have the advantages of reduced ripple content in the output voltage, and it can be used for high power applications. The different types of three-phase controlled rectifiers are three-pulse converters, which are the half-wave controlled rectifiers. Six-pulse converters and 12-pulse converters are all full-wave controlled rectifiers. When we mean controlled rectifiers, the semiconductor device used is a thyristor, that is an SCR, instead of a diode. Rectifiers which convert AC to DC find applications in many areas like DC motor speed control, DC supply for inverters, electrochemical processes, DC traction, and high voltage DC transmission. In the case of a single phase half wave controlled rectifier, a single thyristor is used and a single phase supply is given. The input voltage waveform is shown over here. The output of a single phase half wave controlled rectifier will be a pulse, a single pulse for a duration of 0 to 180 degrees, and during the negative half cycle there will not be any output. If the firing angle is changed, a part of the positive half cycle will be available as the output. In the case of a three-phase half-wave controlled rectifier, three thyristors are used, T1, T2, T3. Each thyristor is connected to one phase of the three-phase supply. Let us now see the operation of the three-phase half-wave controlled rectifier. T1 is connected to R phase, T2 is connected to Y phase, T3 is connected to B phase. The waveform of T1, the voltage waveform of T1 is shown by the red color. The voltage waveform of T2 is given by yellow. T3 is given by blue color. If we observe the input voltage waveform, the thyristor T1 has a positive voltage from 0 to 180 degrees, and from 180 degrees to 360 degrees it is having the negative half cycle. So when the triggering pulse is given to T1, it would start conducting. If the firing pulse is given anywhere between 0 and 180 degrees, the thyristor T1 would conduct, but the thyristor is getting the maximum positive voltage from this point, that is omega t is equal to 30 to omega t is equal to 150 degrees only. Between 0 and 30 degrees and between 150 and 180 degrees, though it has a positive voltage, it will not conduct when the triggering pulse is given. This is because the other two phase thyristors are connected in such a way that they get the negative voltage, and because of that the highest positive voltage for the R phase thyristor is not available. Hence, the thyristor will be conducting from omega t is equal to 30 to 1 omega t is equal to 150 degrees when the firing pulse is given. Similarly, T2 would conduct from 150 to 270 degrees where it gets the highest positive voltage, and T3 would conduct from 270 to 390 degrees where it gets the highest positive voltage. So if the firing pulse is given at the instant where the highest positive voltage is available, we would get three pulses as shown here. So the output voltage of a three-phase half-wave controlled rectifier gives three pulses, hence it is called as a three-pulse converter also. Three-phase half-wave controlled rectifier for various firing angles is shown in this picture. The input waveform, a three-phase waveform, is shown here, and the output of the three-phase half-wave rectifier for a firing angle 0 is 3 pulses as shown over here, and when the firing angle is less than 30 degrees, we can see that the output voltage waveform shown in the black color is a continuous one. And if the firing angle is greater than 30 degrees, the output waveform is discontinuous and it is going to a zero value at some instance. Let us see the operation of the half-wave rectifier for firing angle less than 30 and greater than 30 in the coming slides. When the firing angle is 0 degrees, which corresponds to omega t is equal to 30 degrees, T1 conducts from 30 degrees to 150 degrees, T2 conducts from 150 to 270 degrees, T3 conducts from 270 to 390 degrees. If the firing angle is less than 30 degrees, which means omega t less than 60 degrees, between omega t 30 degrees and 60 degrees, T1 conducts from 30 plus alpha to 150 plus alpha, T2 conducts from 150 plus alpha to 270 plus alpha, T3 conducts from 270 plus alpha to 390 plus alpha. Here we can see that the voltage waveform is continuous. When the firing angle is greater than 30 degrees, the T1 thyristor conducts from 30 plus alpha to 180 degrees where the voltage becomes 0 and T2 conducts from 150 plus alpha to 300 degrees and so on. So when we see the firing angle change, when the firing angle is less than 30 degrees, the output voltage waveform is continuous. When the firing angle is greater than 30 degrees, the output voltage waveform is discontinuous. The average output voltage of a three-phase half-wave control rectifier is given by V0 is equal to 3Vm by 2 pi into cos alpha, where Vm is the maximum value of the line voltage and alpha is the firing angle. The operation of a three-phase half-wave controlled rectifier for various firing angles, say alpha is equal to 0, alpha less than 30 and alpha greater than 30, is explained in this lecture. Thank you. Let us simulate a three-phase half-wave controlled rectifier in this session. We'll open a new file. And for simulating a three-phase half-wave controlled rectifier, we need three single-phase voltage sources. We'll take the sinusoidal voltage source, three voltage sources. We need three thyristors. We can pick the thyristors from the elements, power, switches and thyristors. We can pick the thyristor. We need three thyristors. We'll place them here. And now let us connect the source and the thyristor. We have one thyristor per phase. So we will connect them using the wire. One thyristor is connected to one phase of the source. So now we'll take a wire. We'll connect one thyristor to one phase, the second thyristor to another phase, third thyristor to another phase. And let us connect all the cathodes of the thyristors like this. Now we need the gating signals for the thyristor. We'll take the gating block and place it near one thyristor, each thyristor. The negative of the the other end of the voltage source has to be connected together like this. And to this junction, we will be adding a earth. At times without the earth, the simulation does not work. So we will be connecting to connecting an earth here. And for simulating this circuit, we need a load. We'll take a resistive load and we'll place it here. The excess one can be deleted. Now we'll connect this resistors one end to the cathode's end, the other end to the junction where the voltage sources are connected. This is the circuit, and now the very important thing is the gating pulse, which is to be given to the thyristors. We'll connect the gating blocks to the gate terminal of the thyristors, and we will have a voltage probe to measure the output voltage. To place it here across the load, that is across the resistor. A three-phase half-wave controlled rectifier converts a sinusoidal three-phase voltage into a unidirectional output voltage. Now for that, we need to see that each thyristor conducts at a point where the maximum voltage is available to it. So if we see this thyristor, which is connected to one of the phases, will conduct for a particular time, and after that the voltage available for this would become lesser, so it will not be able to conduct. Regarding the three-phase voltage waveform, not all thyristors will have the peak value all the time. Based on the phase angle between the three voltage sources we have, the maximum value of voltage available for the thyristors will change. So based on the time at which a thyristor gets its peak voltage, it will conduct. Let us give the attributes now. We'll mark this as T1 or TR to be more precise. The thyristor connected to the R phase, and this can be displayed. Then let us mark this thyristor as TY, which is connected to the Y phase, and let us mark this thyristor as TR, which is connected to the R phase. Now let us give the value for the AC voltage source as we can mark this as R phase voltage source, and let us, this being a three-phase supply, this is one of the supplies for the three-phase. We'll just mark it as 325 and have the frequency as 50. Then no other changes done over here. The phase angle is 0 here. In a three-phase supply, each phase has got a phase shift of 120 degrees from the other phase. So now for the first phase, we have given a phase angle as 0. For the second phase, while giving the attributes, the voltage, we will change it to 325, the frequency to 50, and because it is displaced from the R phase by 120 degrees, let us mark it as minus 120 degrees, and we'll display the name By. Then this is the B phase, so here we'll mark the source as VB, change the voltage as 325, change the frequency as 50, and have the phase angle shift as minus 240. That is a shift of 120 degrees from the Y phase. Now we have given three single phase sources. We have given the gating blocks. So let us say that if this is going to conduct, the thyristor is conducting at say 0 degrees, then this thyristor will conduct 120 degrees after that. This thyristor will conduct 240 degrees after the Y phase thyristor. So the attributes what we give for the gating block is, first gating block will give the frequency as 50 hertz. This also we can mark it as GR just to tell that it is connected to the R phase thyristor, and the phase angle can be, the switching points are 2. The switching can happen at 0 and 180 degrees. Mark it as GR. Then we will mark the next thyristor as GY because it is connected to Y phase. Here also we will change the frequency, and here it would conduct from 120 degrees. So instead of 0 and 180 we would put 120, and in a cycle it is up to 360 degrees. So 120, 360 we can put. Display this GY, and then we will take the third thyristor. This would conduct this gating block to the thyristor would be marked as GB. The frequency we change it as 50, and here it is 240, 240 and 360 because in the cycle of one full cycle it ends at 360. So these are the attributes we have given. Now we need all the elements are given here. The resistive load is given an attribute. Say let us mark the load as R and let the ohms be 10 or 100 ohms. Now we need a simulation control. All the elements are now connected. We need a simulation control. We'll place it here. The time for which we need to see the simulation is, let us make it as say 0.05 or even 0.6. Now let us simulate and see. The idea behind this simulation is we have three single phase voltage sources equivalent to three phase voltage source. The input here is AC. At the output, we have to see the output as a unidirectional one, or only the positive halves will be present. So let us simulate and check. So here the problem is we have given the name as GR, that is not allowed. So let me make it as G1 itself. And this I would give it as G2. And this one I can give it as G3. Now let us simulate. Even the names of this are not to be given as TR. So I can give it as T1, T2 and T3, so that the simulation happens. Now let us simulate. We have to see the output. We are seeing the output here. We see that we have only the positive halves being present here. We do not have any negative half cycle. It starts with 0. So here the simulation starts at 0 degrees for the first thyristor. Let us see that if the firing angle is given at a later stage, say 60 for the first thyristor, and 60 plus added for the other thyristors. Let us see what happens. Now let us say the gating block of G1 is changed to 60. That is, the firing angle is given at 60 degrees. For the second thyristor, the attribute given is 60 plus 120 plus 60. So 120 plus 60 is 180. And then let us go in for the third gating block. Here we give the attributes as 240 plus 60, that is 300. And let us now simulate again and see. When we run the simulation, we see the output voltage shifted like this. You have an DC output voltage which is having, these are all called ripples. We do not have any negative half cycle. All the pulses are on the positive side. So thus by using this PSIM, we are able to create a circuit which has a AC input, that too three-phase AC input. Having three thyristors, we get an output which is unidirectional.